present you the paper, EZBFT, Decentralizing Byzantine Fault-Tolerant State Machine Replication. We will explain to you what state machine replication and Byzantine fault-tolerant protocols are, the flaws in existing protocols. Then we'll introduce you to the design and evaluation of the proposed solution, EZBFT, as well as the potential applications of this solution.
State machine replication, which is a method for implementing a fault-tolerant service in distributed system by replicating servers and coordinating client interactions with server replicas. The key issue in SMR is with consensus. So SMR employs consensus protocols to execute commands in total order. The consensus solution this paper focuses on is the Byzantine fault-tolerant protocol, which means if a faulty node does not behave as the system expects, such inconsistency will be detected by other nodes, and they will then try to maintain the correctness of the system. Byzantine failure refers to a type of failure in a distributed system where some of the nodes or components in the system behave in an arbitrary or malicious way, sending different or even contradictory information to different nodes. This failure can occur due to a variety of reasons. As you can see here, the commander sent a tag command to both Lieutenant 1 and 2, but upon receiving his message, Lieutenant 2 sends conflicting information to Lieutenant 1, telling him to retreat. In this case, the commander and the loyal lieutenant must use Byzantine fault-tolerant techniques to identify and isolate the traitorous lieutenant and make the right decision to succeed. Byzantine failures are particularly challenging to deal with because they can cause inconsistencies and conflicts in the data that different nodes have, potentially leading to incorrect decisions or outcomes. Byzantine fault-tolerant protocols are designed to handle Byzantine failures by enabling nodes to reach a consensus on the state of the system, even in the presence of faulty or malicious nodes. BFT is important in trust-essential systems like financial or supply chain management systems, as these systems must continue operating correctly even if some components have failed. So being able to achieve BFT is crucial for gaining trust and confidence in this type of systems among their users and stakeholders. Many existing BFT protocols rely on a fixed set of pre-selected nodes as their primary replicas. In this example, Australia is the pre-selected commander, which is close to client 2 but far from client 1. So the downside is obvious. As client 1 tries to transfer information to the primary replica, it results in a large client-side latency due to the long distance between them. We know that BFT communicates with nodes to get the consensus. So in large-scale network, the distance between nodes can be very long. There can be discrepancy in the communication between nodes, increasing the client-side latency. Primary-based protocols such as EZBFT use various techniques to reduce communication steps. However, those techniques do not reduce the client-side latency in a geo-scale setting, where the latency per communication step is as important as the number of communication steps. This way, a protocol can achieve significant cost savings if the latency incurred during a communication step can be reduced. However, when we are speaking of geo-scale networks, while the clients that are geographically nearest to the primary may observe optimal client-side latency, the same is not true for distant clients. A distant client will incur higher latency for the first communication step of sending the request to the primary. And additionally, the traditional approach of primary-based design limits throughput as the primary carries significantly higher load. Therefore, making a geo-scale sufficient BFT protocol will have to resolve these challenges in the client-side latency, communication, and concurrency. So our proposed solution, EZBFT, is a leaderless protocol. In EZBFT, instead of sticking to Australia, a client can send its request to the nearest replica and can continue to do so as long as the replica is correct. And the replica can then undertake the task of finding an order among all the concurrent requests in the system, executing the request on the shared state, and return the result. As we mentioned earlier, instead of relying on fixed leader node, EZBFT, being a leaderless protocol, chooses a committee of nodes randomly to participate in the consensus process simultaneously, which increases concurrency, ensures optimal client-side latencies, and improves server-side throughput. Client also gets involved in the consensus process at the end to ensure a total order. Normally, communication takes 3 steps, but in case of defaults, EZBFT would take 2 extra steps to resolve it. With these modifications, EZBFT can handle BFT and disagreements better than traditional BFT protocols, and it can be applied to geoscale networks.
Our system consists of a set of nodes that are the clients and the replicas. Each of these nodes have their own cryptographic signatures and that the faulty nodes cannot break. We also require at least 3 F+1 replica nodes to handle F Byzantine faults. We have 2 quorums, a fast quorum and a slow quorum. A quorum is basically a set of nodes that work together in making the consensus decision. So the fast quorum consists of 3 F+1 replicas, while the slow quorum consists of at least 2 F+1 replicas to work towards achieving a consensus. Before I get into the details about the protocol, I'd like to introduce some terms that we will be using frequently. Command interference. When 2 or more commands are to be executed in a same replica node, we call it command interference. To keep track of these interferences, each node has a set of all the commands that interfere, and we call it the dependency set. All commands are assigned a sequence number to establish an order and to settle conflicts when required. All the replica nodes also has an instance space, which is nothing but a sequence of number slots where we assign the commands to. We have 2 main protocols, the fast path protocol and the slow path protocol. Fast path protocol is used when there is no contention and no Byzantine failures, while the slow path protocol is used when we have either a contention or Byzantine faults. It only takes 3 communication steps for the client to deliver the message in fast path protocol, while it requires 2 extra additional steps to handle faults in slow path protocol. Now let's look into the fast path protocol in detail. Here we have a user, a client, and 4 replica nodes, of which R0 is chosen by the client as the command leader because it's closest to it and provides optimal latency. When the user queries for the information, the client, it sends a request to the command leader to execute the command. R0, on receiving the request, it assigns the command a place in its instance space. Since it's the first command that R0 is receiving, it assigns the slot as 0 in its instance space, and there is no command interference, so the dependency set here is empty. The command is assigned a sequence number 1. After figuring out these metadata, R0, it sends the information to all the other replicas. The replicas, on receiving the spec order, speculates that the order it has received is correct and all the other replicas are in agreement. All the replicas then execute the command. We call this speculative execution, and the final execution occurs only when the client approves of the final result. The replicas, on receiving the order, checks the dependency set, and if there is any contention, it updates the dependency set and the sequence number. But for the fastpath protocol, we do not have any conflict, so the dependency set is empty, and the sequence number for the command is 1. After executing the command, the replicas reply to the client with the spec reply message, which consists of the results. The client looks at all the replies to see if they match. In fastpath protocol, due to lack of fault and conflicts, all the replies match. The client then sends the result received from the replicas to the requesting user and then sends a commit fast message to the replicas for the final execution of the command. What we can see here is the client receives the result in 3 steps. The result received after speculative execution of the command is equal to the final execution, and hence no extra step is required by the client to deliver the message. Now let's dive into the slow path protocol. It is triggered when the client receives unequal or insufficient spec reply messages. This is an example of contention, that is, when there is a disagreement between the replicas. Here we have 2 clients that sends a request to its nearest replica for the execution of the respective commands L1 and L2. The command leader gathers the values for the dependency set, sequence number, and assigns each command in their instance spaces. So for R0, the dependency set for L1 is empty because this is the first command R0 is executing, and the sequence number for L1 is 1, and it is assigned a slot 0 in the instance space. And the same goes for R1 for the execution of L2. Now let's assume that R2 first receives the order from R0 and it updates its metadata. Likewise, now R1 sends spec order and its metadata to both R0 and R2 to execute the command L2. This is when we have interference because R0 and R2, they've already received a request to execute L1, and in response to that, they updated their dependency set. But now they have received another request, that is to execute L2, and the dependency set looks as follows. For the execution of L2, L1 must be executed first. So the dependency set of L2 contains L1, and L2 is assigned a sequence number of 2. Now let's focus on executing command 1. For R0 and R2, the dependency set is empty because they will be executing L1 first, and the sequence number is 1 for the command L1. But for R1, the dependency set contains L2 because it received the request to execute L2 first, and the sequence number for L2 is 1, and hence the sequence number for L1 will be 2. So when the replica sends the spec reply message to the client, it finds the disagreement in the replies. So the client creates its own order that L2 will be executed first. That is, the sequence number for L1 is equals to 2. So the client chooses the sequence number on the basis of the largest sequence number it receives. So that is 2. And hence, according to client 1, the command L1 will be executed second, and the command L2 will be executed first. The same thing happens in the reply the client 2 receives. There is a mismatch here, and hence the client enforces a new order with a commit message. So the new order is, it selects a sequence number for the execution of L2 that is the largest of all the sequence number it has received, that is equals to 2. So what we observe here is that both the commands have the same sequence number in the end. The replicas, they wait for all the commit messages, one from client 1 and the other from client 2. And what we can observe is a circular dependency is formed, meaning that both L1 and L2 have the same sequence number and they are dependent on each other. To execute L1, we need to execute L2 and vice versa. The replicas, they break the cycle in the end using the replica ID, and hence we execute L1 first and then L2. The result of the execution is sent back to the client, and the client replies to the user. We looked into how the system handled contention. Now let's look at how it handles the Byzantine fault. This is the same example as before, but I've added a faulty node, R3. R0 and R2, they receive a request to execute L1 first, and R1 and R3, they receive a request to execute L2 first, and the metadata is updated likewise. After that, R1, it sends a spec order to execute the command L2 to R0 and R2. If we just look at the top 2 nodes, to execute L2, they must execute L1. Hence, the dependency set and sequence number is updated likewise. When the node sends the result of the execution to the client, the faulty node R3, it lies by saying that it hasn't received the request to execute L2 to create an agreement. We can see the information in the green is what the R3 should have sent to the client, but it instead sends the one in red. The client, on getting the reply, sees that there is an agreement, and hence our final order of execution is that L1 will be assigned a sequence number of 1. When the replies are sent to the client 2, the node behaves normally, but since there's command interference, like we saw in the previous example, the final order for L2 here is that L1 will be executed first and then L2. Hence, in the end, L1 has a sequence number of 1 and L2 has a sequence number of 2. All the replicas obey this, and hence we have a total ordering even when there is Byzantine fault. When a command leader is given a command to execute, it becomes the owner of the command. What happens when the command leader is faulty? We need to change the owner of the command. So when the client sends the execute command request to the command leader, it also sets a timer, and if it does not hear back from the replicas, it sends a request to the replicas with the original request it sent to the command leader. If the request matches, then the same is sent back to the client, or else the replica sets a timer and sends a resend request to the command leader. If the command leader does not reply in time, the replica, they initiate a owner change protocol. When other replicas also receive at least F+1 owner change message, the owner change protocol goes into effect. The replicas, they send a message to the client showing the proof of misbehavior from the command leader to change the owner, and the client, it verifies the misbehavior by checking all the replies it has received so far, and then a new owner is chosen according to its owner number. This is the entirety of how EZBFT works and how it handles contention
in Byzantine fault using a leaderless protocol.
We will evaluate the existing protocols and EZBFT, the chosen protocol, in 3 different categories: client-side latency, client scalability, and server-side throughput. Firstly, we will start with the client-side latency. The goal in here is to maintain, is to find out the protocol which has the lower client-side latency. Firstly, we will set the primary location to the US East Virginia. For 3 primary based protocols were used here: GZIVA, FAB, and PBFT, and EZBFT on different contention level were used for this experiment. The contention process, for example, 2% means that 2% of the requests issued by the clients target the same key, and the remaining 90% requests target clients' own or non-overlapping set of keys. We can see that the PBFT performed worst because, as mentioned earlier, it takes 5 communication steps. FAB performed better than PBFT because it takes 4 communication steps. GZIVA outperformed all the primary based protocols because it takes only 3 communication steps. In Virginia, EZBFT performed similar to the GZIVA, whereas it performed better when the region was different than Virginia, which is Japan, Mumbai, and Australia. So for the second experiment, we wanted to show that with the moving of primary location, will there be effect in client-side latency or not? So we only take here GZIVA and EZBFT for this experiment because from the previous experiment, we know that GZIVA outperformed the primary based protocols. So here, if we look into Mumbai, which is now the primary reset location, the latency of GZIVA is way higher than EZBFT. In actual, EZBFT's latency lowered by 45% than GZIVA. So it proves that the leaderless feature of EZBFT is better fit for geo-scale deployments. The second evaluation category is client scalability. The goal in here is to maintain the low client-side latency with increase in the number of the connected circuits. So for this experiment, different protocols were deployed in different regions, Virginia, Japan, Mumbai, and Australia, and the client-side latency per region were measured with varying number of connected circuits. So if we look into the Mumbai region, for instance, here EZBFT at contention level 0 and at contention 50%, it is stable with the number of connected circuits. However, GZBF, GZVA latency shoots up when the connected circuits reaches 100. So this proves that EZBFT was able to maintain low client-side latency with the increase in the number of connected circuits. The third evaluation category is server-side throughput. The goal here is to maintain the peak throughput of the protocols. So for this, we co-located 10 circuits with the primary replica in the US East. And so for this experiment, the clients would send requests continuously and asynchronously before receiving replies. When the clients are placed in all the regions, EZBFT throughout throughput increases by as much as 4 times, as all the EZBFT replicas are able to process and deliver requests concurrently. So the leaderless characteristics allows all replicas to feed requests into the system, which increases the overall throughput. In this case, 2 EZBFT has power slightly better than the other primary based protocol, whereas EZBFT was performed better. The throughput increased by 4 times. Now we can use this into the real world application. We can use this in the financial sector, where it can improve the speed and efficacy of cross-border payments and reduce time and cost. It can also be used in supply chain management to track and verify the movement of goods across different stages of the supply chain, or quickly and efficiently reach concession on the status, and improve transparency, reduce risk of fraud or errors. So in conclusion, so we start with the problem that we wanted to build a Byzantine fault tolerance that can achieve low client-side latency and high server-side throughput in a large-scale network. So we have a solution, which is EZBFT. And as I discussed earlier, that we were able to achieve low client-side latency and high server-side throughput.